warahmatullahi wabarakatuh and salam sejahtera. For this video, we discuss chapter 2.2, charging and discharging of capacitors. You should watch the previous the two videos first, which is about 2.1 and in some introduction on capacitors before you watch this one. So for this subtopic, you will learn about the physical meaning of the time constant. So I think this one is quite a new quantity for you guys, new term. And then you need to be able to sketch and explain the characteristic of QT and IT graph for charging and discharging of a capacitor. So we have charging and discharging capacitor, and then you need to be able to use this formula. Q equals to Q naught equals to E exponent negative T over RC for charging, and that one's for discharging. So this one is actually very similar to the one that you did in your experiment 1, except that one is just for discharging of a capacitor. So this is an example of charging and discharging pin circuit. So for charging, it is connected to a power supply. The switch is closed and you will see the electron flow initially lah. And then this one is for discharging. Actually, the switch is still closed, except now they remove the power supply. So when they remove the power supply, the circuit need to be complete as well lah. Okay, we discuss in detail very soon, but before that, I just want to introduce the time constant. What is actually the time constant? Time constant is a scalar quantity. It is a measurement of how quickly the capacitor charges or discharges. So sometimes it has a different meaning for charging and discharging, but we'll go into that very soon as well. Okay, let's say we start with the charging process. You can imagine, let's say if I have a capacitor, maybe I can draw it slightly to the left. Oops. Okay. Okay, so if I draw it like this, so that one is my power supply, and then it is connected through a resistor here. I think actually almost all the circuit contains a resistor. If you want to have a current, you need to have a resistor. And then it goes into a capacitor. Then initially it is open like this. Okay, so what happened here is that initially, before the capacitor is being charged, before the capacitor is being charged, you will expect you have a balance charge on the capacitor. So like positive over here, negative, positive, and negative. Over here maybe negative, positive, negative, positive. So basically the balance. Okay, once the switch is closed, so the circuit is complete. What will happen, because we have EMF over here where it will force the electron to move, electron will flow in this direction. It will come out from the negative terminals. So this is direction of electron, and it will accumulate over here. So basically it will go over there. So you can see that once the electron increase over here, so maybe I have more electrons here, and here, what will happen at the same time, we try to push the electron away from this side. We push, and then basically it will move all the electrons from that side. So you left with, at the end of the day, you left with all the positives over here. This one actually still have the positive, but because the numbers of positive is very small, basically we ignore that one. So one plate consists of all the electrons, another plate there's no electron. Okay, so electron flow over there. And eventually, initially, the potential difference across the capacitor may be about 0. when you have the electron being pushed away, then you have a potential difference. You start to have a potential difference lah. And the potential difference will increase, and eventually the potential difference will be the same with that one. Once the potential difference is the same, so this one don't have enough force to push the electron anymore. So what happened here is that during the charging process, I'm going to erase this one first. Okay. During the charging process, initially you have a balance charge, and then it start to increase, and then it reach a maximum value. That one is what we call Q0. So this is when the potential difference is the same with the power supply. Okay, so it start from 0 charge, and then it increase, and eventually it reach 0. So it makes sense lah. How about the current? So the current actually measured across the resistor. So normally they will put the ammeter over there. Change back to the blue. Okay, so the moment when the switch is closed, you basically have a very large I. That's what we call I naught, the maximum I, because you have a maximum I, because at that time you have flow of electron, the maximum lah. But then once the electron is filled up in the negative terminal over here, so the flow of electron, you can imagine that it becomes slower, going in this direction. We start to push it a little bit slower, and eventually it becomes 0. So electron move initially very fast, but then it decrease, resulting in decrease in magnitude of current, and eventually it reach 0 when the voltage here is the same with the voltage over there. This one is the same with the power supply. So there's no more electron flows. When there's no more electron flows, there's no more current, because I is equals to dq over dt. So it depends on the flow of electron. Okay, because of that, we have two sets of equations to represent the charging process of Q and charging process of I. So I'm going to write it over here. So for Q, this is important formula. Q equals to Q0 1 minus exponent T over RC. Okay, in fact, the RC is actually the tau, where tau is equals to RC lah. This is a time constant, equals to RC. On the other hand, for I, current in resistor, we have I equals to I naught exponent negative time over RC. So if you want to memorize the formula, the easiest way is that if you have a initially very high gradient over there and decrease, that one is 1 minus something. This is how I memorize things. Q0 and I naught is actually the maximum charge and maximum current. I have to write it over here. So Q0, I naught is maximum Q, maximum current, R is the resistor, and C is the capacitance. Okay, now maybe we can try to look at the discharging process. Okay, let's erase this one first. Okay, this one for discharging process. Okay, now you already have a capacitor that being fully charged. It is still connected through a resistor, but now you remove the power supply. Okay, so initially it is not being, the circuit is being open, so you have charge that is fully charged over here at the capacitor there. So basically at that time you have a Q naught. Okay, the moment that we close this switch, okay, just now I drew positive there, negative there, so positive here, negative here. The moment we close the switch, what will happen is that the electron will start to flow back. So all the electron being pushed in this side, so we go through the resistor and to the other plates punya position. So what will happen is that the charge will decrease. Okay, the charge will decrease and eventually it will become 0. Okay. Then at the same time, the current will flow, but now it will flow in the opposite direction. Initially, you can imagine that electron over here is accumulate over here. The moment that the switch is closed, all the electron will try to rush to the other side. So you have a high magnitude of current, and then as it goes, as the time increase, the charge start to slow down. So you can imagine that the magnitude of current decreasing, and eventually it becomes 0 when the potential is 0. So the idea is that you have high magnitude initially, and then at the end there you have I equals to 0. The key thing here is that the direction of the current is now the opposite of the charging process. That's why I draw it over here, negative over there. So for the discharging Q, I have a formula of Q equals to Q naught E negative T over RC, and this one is actually I equals to negative I naught exponent negative T over RC. Okay, the term that we use is the same lah. RC basically the resistor, the capacitance, maximum Q, maximum I, Q naught, I naught. Okay, the thing here, for calculation purpose, we ignore the negative here. For calculation, ignore negative. So basically, we just ignore lah. The reason is that because the negative indicates the direction of current. So if you want to determine the direction, you can straight away look at the circuit. Okay. The one thing that I want to point out is about the tau. Okay, for the first one, the tau is actually represent the value over here. 0.63 out of Q naught. This is your tau. And over here is 0.37 of I naught. For this one is 0.37, and this one is 0.37 as well. Okay, if you look at your notes, okay, tau is defined, okay, this one we have to go through. Okay, for charging, tau is defined as the time required for the capacitor to reach capacitance 0.63, 63% of its maximum charge. Okay, but for the current, that one is for charge. For the current, defined as the time required for the current drops to 0.37. So it's a little bit different in meanings over there. The tau for discharging defined as the time required for the charge on the capacitor across it to decrease to 0.37. Okay, this one it doesn't state. It doesn't state the tau anymore. Okay. Anyway, over here you can see that only for the charging process, charging capacitor, the tau for charge represent the time taken. Sorry, I'm talking about this one. The time taken for the time taken to reach 0.63 ataupun 63% of your Q naught. The time taken to charge lah. The rest would be discharging. The rest would be decreasing, sorry. So for this one, it's the time taken to reach, to decrease to 0.37%. Sorry, 0.37 or 37%. This one also the same. Decrease, decrease. So the only time it increase is 0.63 and then the rest is 0.37. Okay, let's try to look at one of the example here. In the excuse me. In the RC circuit shown in figure below, the battery has fully charged the capacitor. By the way, you can try to go through your lecture notes. Basically the same thing that I explained just now, just that I tried to simplify things. The most important thing here is that you have to be able to identify the correct formula that you want to use. So let's say in the exam, they state the situation whether it's charging or discharging, and then you have to choose whether you want to choose Q equals to Q naught 1 minus E, or you want to choose Q equals to Q naught E. So that one is depend on the whether it's a charging or discharging process. So the important thing here is that you have to be able to differentiate. And then you need to be able to draw as well. Okay, back to the example. In the RC circuit, the battery has fully charged the capacitor. When the time is 0, a switch S is thrown from position A to B. So initially, A to B, I think it's initially, I think this is position A. And then initially it's over here, and then they throw it over here. You could. The battery voltage V0 is 12 volts. Oh, betul lah. A to B. Okay, saya salah. Nampak? Correct. I'm going to change the color. Okay, doesn't make much difference. Okay. So, the V0 here is 12 volt. And the capacitance is 3 microfarad. Okay, in exam you can always try to redraw the circuit. The current I is observed to decrease to 0.45 of its initial value in 60 microseconds. Determine the values of R. Okay, first thing first, you have to identify whether this one is actually charging or discharging punya process. Oh, they want to find R first. Okay, that makes sense. So if you look over here, initially it is at A. So after a few seconds or a few minutes, then you expect the capacitor to be fully charged. Okay, Now the question state that it is being changed from A to B. What will happen is that you have this part over here as your circuit. So this one, there's no power supply. You have a resistor and you have a capacitor in this particular circuit. So it shows that this one is actually a discharging process. Okay, and the important things here is that the battery voltage V0 is 12, the current I is observed to decrease to 0.45 of its initial value in 60 microsecond. If I want to take out the information, I can write here is V0 equals to 12 volt. Capacitance is equals to 3 microvolt, 3 microfarad. Okay. And then another important thing is that when the current decrease to 0.45 I when from the initial 60 second, t equals to 60 microsecond. Okay, maybe I can try to redraw the graph, the circuit. Okay, and then the graph should look something like, because we are talking about, if you want to talk about I, current, discharging process, this one, current is over there, but for the calculation's sake, maybe we can just focus on the positive one. Mana tadi soalannya? Okay, here. So the direction of current should look something like this. Okay, the formula that we need to use is I equals to I naught exponent negative T over RC. The first question, they want you to find A. They want to find R. So I can substitute inside here. So basically, I choose this formula because this one represent the discharging of current. Okay, you should, if it depends on this graph, it should have negative, but for calculation purpose, we ignore the negative one. So substitute this value here, 0.45 I naught equals to I naught exponent negative 60 times 10 negative 6 over R. Capacitance is 3 microfarad. Okay, I can cancel out the I naught and I can take the ln, which is ln 0.45. In exam, normally you have to solve it like this. Now you have to take the ln. Once I take the ln, I have ln E, and then up here I can bring it down there. So basically I have negative 60 times 10 negative 6 over 3 times 10 negative 6 R. Okay, you can solve this one and find the R straight away. So ln E is equals to 1. Ln 0.45 is actually equals to negative 0.799. Okay, so equals to negative 60 times 10 negative 6 over 3 times 10 negative 6 R. Cancel out the negative. So you left it 60 exponent negative 6 divided by 3 exponent negative 6 divided by 0.799. I got here is 25.03. Okay, just check the answer. Yeah, I think that's about right. This one should be 24.03. Okay, the next question, they want to find the time constant tau. Okay, this one is the easiest part. So this one for A. For B, if I want to calculate tau, which is equals to RC, you can simply multiply. R is 25.03. This one is 3 microfarad. 3 times 10 negative 6. So get 25.03 multiplied by 3 10 negative 6. 7.51 times 10 negative 5. The unit will be second because that one is just a time, t. So if I compare the answer here, yeah, same answer. Okay, question C. The value of Q, the charge on the capacitor at t equals to 0. Okay, if you are looking at the graph, if you try to draw a graph here, okay, we go back to our notes just now. For discharging, our graph for Q would look something like that. So just redraw it over here. My graph of Q will look something like this. So this one is I against time. This one is Q against time. So Q0 is over here, where the time is 0. Okay, how do I calculate Q0? I can straight away calculate Q0 using C equals to Q over V. If this one is C, basically the total lah, C effective. This one is V, V0. This one will be my Q0. That one, sometimes I call that one as VT as well. So my Q0 is equals to C, which is 3 times 10 negative 6. We only have one capacitor here. Multiply with 12. So V0. So the Q0 is equals to 3 multiply with 12. Press it again. 3.6 times 10 negative 5. Unit will be coulomb. And then the last question, okay, this one they just want to state this one when t is equals to 0, which we already know based on our graph. Okay, the value of Q at t equals to 100 microsecond. So the last one, when t is equals to 100 microsecond. Is it correct? Microsecond, yes. You're looking back to our lecture notes. For discharging, we have to use this equation. Q equals to Q0 exponent negative t over RC. Okay, so the only time that you have 1 minus exponent is when you have a charging process for charge. Even for current, you don't have that one. Only for charge. Okay, this one will Q equals to Q0. What I need to do is substitute all the values. That one is negative 5. Okay. Negative 100 times 10 negative 6 divided by RC that we already calculated, 7.51 times 10 negative 5. Now you just have to press your calculator. My suggestion is that you solve the exponent part first. So again, it depends on your calculator. Personally, I just love to do one by one. Okay, don't forget the negative exponent. Got negative exponent, negative something. Okay, I got here, it's 9.5 times 10 negative 6. Okay, which is lower than the Q0. What does it mean? That you can imagine that I have a graph like this. So here is my Q0, which is at the values of 3.6 times 10 negative 5. So over a certain period of time, maybe right over here, I'm not sure. I have Q when t is equals to 100 microsecond. So the Q should be much lower lah. Okay, this is how it looks like. So everything should make sense. Okay, and I just want to repeat, the important parts here, once you get the question, the first thing that you need to do is that you have to determine whether it's charging or discharging process. Once you determine, maybe you can try to draw the graph, just the shape of the graph of Q and I against T, so that you get an idea what formula you want to use. Normally I memorize it like that. From the graph, I know what kind of formula that I need to use. Just write down the formula, and then you just have to solve the question one by one. Okay, I think that's all for this subtopic. So this one is end of part 3. So next video, we discuss the final part of the chapter. We got a little bit more to go. Oh, banyak lagi. Okay, it's okay. Thank you everyone.